Good day to you. What we're doing today is some one-dimensional momentum problems. So these are three different collisions in all along a line. So there's no 2Ds, it's just everything's in one line. But I'm going to do three different types of collision so you can see kind of how the math and particularly the signs are going to work out with different types of collisions. All right, so our first one. A 25-gram bullet enters a 2.35 kilogram watermelon and embeds itself in the melon, so it stays in the melon. The melon is immediately set into motion with a speed of 3.82 meters per second. The bullet remains lodged inside the melon. What was the entry speed of the bullet? All right, there's our question. So we need to do a picture, and with momentum, just like with energy, it's really important to do initial and final, but it's hard to put these on one picture. So I strongly encourage you to do two separate pictures for momentum problems, the initial and then the final. So here we have a bullet, there's my bullet, going into a watermelon. And initially, the bullet is traveling and the watermelon is at rest. Then the bullet stays in the watermelon, and both of them are moving. So we have the bullet moving initially, watermelon at rest, and then they're joined together, moving this way. If you drew them moving this way, no problem. You can solve it that way as well. What do we know? We know the mass of the bullet is 25 grams, and I'm going to convert that right away because I need kilograms. 0.025 kilograms. The mass of the watermelon is 2.35 kilograms. What do we know? The final velocity of the watermelon we're given as 3.82 meters per second, and we want to know what is the entry speed of the bullet. So what's the initial speed of the bullet when it hits the watermelon? All right, picture with initial and final. Knowns, unknown. We are dealing with conservation of momentum here, so we just need to know that the initial momentum and the final momentum have to be equal. Initial has to equal final. We have two objects, which means we need to deal with the initial momentum of the bullet and the initial momentum of the watermelon, the final momentum of the bullet, and the final momentum of the watermelon. Okay, so this will be the mass of the bullet times the initial velocity of the bullet. This is the mass of the watermelon times the initial velocity of the watermelon equals bullet final V. It's really hard to keep track of all these subscripts. V final bullet plus mass watermelon times V final watermelon. All right. So we have two objects, and we have both initial and final, which means we have four terms to take care of. Bullet initial, watermelon initial, bullet final, watermelon final. The watermelon is at rest to start, which means that its velocity is 0. This whole term drops out. It does not have any momentum. So it was at rest. There is no initial momentum of the watermelon. What do we know? We know the mass of the bullet. We're looking for this. This is our question mark. We know the mass of the bullet. We know the mass of the watermelon. And we're given the final velocity of the watermelon. Okay, so it looks like we have everything except the final velocity of the bullet. And then you look at this picture and you say, we know the final velocity of the bullet, right? The final velocity of the bullet has to equal the final velocity of the watermelon because they're together. They are squished together. So they better have the same velocity. All right, so on this side, I can say those are the same, which means I have MB times V final plus MW times V final, which is, I'm just going to factor out that V final. It's the combined mass times V final. And if you think about it, what's the momentum in this picture? Well, it's mass plus mass. Combined mass moving at a certain velocity. So you can either do it separately like this, or you can say, well, they're together, so it's the combined mass moving at some velocity. I don't care which way it goes. Here we've got mass bullet v initial bullet. All right, so we know everything, don't we, except V initial bullet. Mass of the bullet was 0.025 times V initial bullet equals 0.025 plus 2.35 V final 3.82. So add those together, multiply by 3.28, divide that by 0.025 to get the muzzle velocity of the bullet, which is usually pretty fast. Yep, 363 meters per second. That is 1/3 of a kilometer in a second. Pretty darn fast. These things do tend to fly. Okay, so is that a reasonable answer for a bullet? Yeah. Did we answer the question? What was the entry speed of the bullet? Yep, we did. All right, so that's our first problem. We have a situation where we have an object at rest and an object moving. They stick together, and then they both end up moving together at a much, much slower speed. So we started with the bullet at 363 meters per second, and we end up with both of them moving at about 4 meters per second. So pretty darn good. All right, so that's our first one. Now, in this next one, we are going to have the bullet fired at the watermelon, and we're going to have the bullet go through the watermelon. So it's going to pass through the watermelon. Okay, that's still all true. I'm not going to get rid of everything. Oh, I guess I could have kept that one too. Oh well. Oh well. All right. So now we have the same thing with the initial momentum of the watermelon. That's still 0 because it is at rest. But our final is going to be different because they're not tied together anymore. What we have going on here is the watermelon is going to be moving, and then the bullet went through it and it's still moving. Okay, so a 25-gram bullet enters a 2.3 kilogram watermelon with a speed of 217 meters per second. So the initial speed of the bullet, 217 meters per second, and it exits the watermelon at the opposite side of the watermelon with a speed of 109 meters per second. So the final velocity of the bullet is 109 meters per second. Melon is originally at rest. What is the final speed of the watermelon? All right. So the bullet went through and it gave up some of its momentum to the watermelon. So it still has momentum, and whatever it gave up is going to happen right there. Okay, we still have this. That's conservation of momentum, which means we still have this. And the watermelon's at rest to start with, so that's still true. Let's do the next one. All right, so mass of the bullet, V initial bullet. Okay, I can skip that. Equals mass of the bullet, V final bullet, plus mass watermelon times V final watermelon. Okay, so plus 0 is really what it is. We want to know V final watermelon. We want to know this. We know the mass of the bullet. We know V initial bullet. We know the mass of the bullet. We know V final bullet. We know the mass of the watermelon. This one's pretty straightforward. All right, so if we do this, what do we have? We have the mass of the bullet, 0.025, times V initial, 217, equals 0.025, 109, plus 2.35 times V final watermelon. And so if you just take a look at this, this is the initial momentum of the bullet. This is the final momentum of the bullet. It dropped. We went from this times 217 to this times 109. So where did that momentum go? It went into the watermelon. So whatever is the difference between these two is going to give us the momentum of the watermelon, and from there we can get the velocity of the watermelon. So if you do that, you get final velocity of the watermelon of 1.15 meters per second. Reasonable? Sure. I mean, there was a lot of momentum to start with, 217 meters per second. So even though it's a very small mass, we have a very large velocity. And it gives up almost half of its velocity. So it gives up almost half of its momentum, that means. to the watermelon, which is 1 to 100 times bigger. So it gave up about half of its momentum to something 100 times bigger, which means, yeah, instead of dropping 100 meters per second, 100 divided by 100 gives us about 1. So, kind of makes sense. It's a reasonable answer, and we answered the question. What is the speed of the melon as the bullet leaves the opposite side? All right. Keep that 1.15 number in mind, because this next one, I'm going to want you to make a prediction about that final. So this one was 1.15 meters per second when it went through. So that's where the bullet ended up going that way, and the watermelon ended up moving as well. Okay, before I erase, let's just erase this part. Save myself a little writing. Alright, so I do need to get rid of the blue because I don't know what we're looking for this time. Okay. Part 3. Now, we have a 25-gram bullet is fired at a 2.35 kilogram watermelon. And this is a special watermelon. It was developed by the Buckaroo Banzai team, look it up, to withstand airdrops from like a mile high. So it's got a really tough rind, which means that instead of the bullet going into it, the bullet bounces off. So what's going to happen here is the bullet bounces off and goes that way. And now what's going to happen to the watermelon? Which direction do you think the watermelon's going to go? Here's where we make a good prediction based on, just being reasonable about it, and then let the math tell us if we are right. So I'm making a pretty darn good guess that the watermelon's going this way. It has to. The total momentum that we started with was something going to the right, which means the total momentum at the end has to be going to the right. This has momentum to the left. So if we end up with total momentum to the right, this better be going to the right. And we want to know what that final velocity of the watermelon is. And we're given the initial speed of the bullet was 217 again. And it bounces off. The final velocity of the bullet is 100 meters per second. We want to know what that watermelon speed is. All right, if you just ran through and put all these numbers down, you're almost correct. What's the direction of that bullet? It is now going to the left. We have to take into account the direction. Everything we've done so far has been moving to the right, so it's been positive. Now we have something moving to the left, which means we have a negative velocity. In energy, it didn't matter what the direction was because we squared the velocity. It always came out positive. With momentum, it's just mass times velocity. We have to take into account the direction. So, final velocity of the bullet is negative because it's going to the left. Now, this is still true. This is still true. This is still true. What are we looking for? We are looking for the final velocity of the watermelon. I guess I didn't need to erase that. We know the mass of the bullet, the mass of the bullet, the mass of the watermelon. We know initial velocity of the bullet and the final velocity of the bullet. Turns out it's almost identical to the last one. Mass of the bullet is 0.025. Initial velocity is 217. This is exactly what we had before. Mass of the bullet, 0.025. Final velocity, negative 100, plus 2.35 times the final velocity of the watermelon. So again, don't lose track of that negative. It's very important. So we're going to take this number, and now this is a negative number, so when we bring it over, we're adding it to the other side. I don't remember if I actually have the numbers. Nope, I don't. So we're going to take this and then add it to this, because this is negative. To bring it over, we have to add it. And if you do the math here, all right, predict. Do you think when the bullet bounces off that the velocity of the watermelon is going to be bigger than 1.5 when it went through, equal, the same, or smaller than 1.15? So when the bullet bounces off, does that give more velocity to the watermelon, less velocity to the watermelon, or the same amount? So give that a thought. Make your prediction. Think about, well, this is my gut response. Does that match with what I'm kind of thinking about this? Okay, let's see. And then we do the math, and what we come out with is 3.4 meters per second. Bigger. When the bullet went through, it gave up a little bit of its momentum to the watermelon. Now we have a certain amount of initial momentum. I'm just going to make up a number just so we can see what it would be like. So let's say we start with 75 momentum. I don't care what the unit is, let's just say we have 75. When we did, and this is plus 75, when we did the watermelons moving and the bullets moving, this might have plus 25, this might have plus 50. They both have positive momentum because they're both going to the right. Same initial condition, so if we start with 75 total momentum to the right, now we have some here. If this is negative, let's see, it ended up with, was it a faster speed or a slower speed? 109 to 100, about the same. So this would be about negative 50. What does the momentum of the watermelon have to be? Well, the total has to be 75. If we're here at negative 50, how do we get a total of 75? Well, the watermelon has to have 75 plus the 50. So this would have to have 125 units of momentum compared to the 25 that it had before. And again, those are just made up numbers, but I just want to see, you know, what the conceptual part of it is. So it does make sense that when the bullet bounces off, the watermelon is traveling faster because it's got to deal with not only the original momentum of the bullet, but it also has to counteract or take into account this new negative momentum. So we've got all our answers, right? How fast is it going after the bullet bounces off? 3.4 meters per second. So there are 3 different collisions, and using conservation of momentum, we can figure out whatever we need to about this situation. We just have to make sure we're always dealing with our direction. I tend to have things going to the right, which means we tend to have positive, but you can't always assume everything's positive. This one was going to the left. It had a negative velocity. Momentum is a vector, and we're going to see that when we get into 2 dimensions, because we'll have to deal with up, down, and left, right. And then it's going to be even more interesting. Vectors. Go back to vectors. I know you love vectors. So there is our momentum problem. I would call this just a basic sea level momentum problem, and we've answered the question. It's reasonable. They were all, the 3 velocities were all in the same range, 3.8, 1.1, 3.4. They are reasonable. So I think we've got it. All right, good job.